All right, so my name is Victor Klang. I work for a company called Typesafe. We're the company with the software stack for applications that scale. And I happen to be the tech lead of a project called Akka, which is a part of Typesafe. And I'm here today to talk to you about Akka and how to scale software both up and out. So, without further ado, Akka, besides being a really beautiful mountain in the north of Sweden, it also happens to be a goddess of all beauty and wisdom in the world. And also a software project, but in that order. And Akka is built to be a runtime and a middleware platform for doing concurrency and scalability on the JVM. So it's built using your normal JVM stuff. So Java util concurrent and all the magic we can do with that. But it's also built in a language called Scala. So how many of you are familiar with the language Scala? Yay, that's like everybody. Cool. So what's important is that we don't really target Scala only. So we think it's very important to sort of be open, like letting everybody in. So we want to make sure that we have a really good Java interop story. So we want you to be able to leverage what you already know. So if you're a Java developer, you've spent a lot of time learning Java, you have a lot of ecosystem, you have a lot of experiences, and you have a lot of tools that you're already using. So with Akka, you can use it from Java today as much as you want. You have the option of using it with Scala. Scala lets you do some stuff that Java doesn't. But it also allows you to integrate with what you already have, like your infrastructure and your deployment scenarios, your web apps and application containers. So you might ask, okay, is anybody really using this? Well, there's a couple of Akka production users just to get you started. I'll take some water. You might recognize some of these companies there. So this isn't something that just appeared out of nowhere and nobody's using it. This is really solving real problems for real companies in the world. So what is the purpose of Akka in itself? Well, we want you to be able to program at a higher level. So if any of you have done any concurrency and parallelism work on Java on the JVM before, you know that normally you end up with a lot of coordination code within your business logic. You end up with locks, you end up with synchronized blocks, and you're sort of mixing concerns in your code. Normally, it also means that your code is very tightly coupled with how it's executed. So it's really fixed, like how many threads are we using? Where are we deploying it to? It becomes a part of how your application is written. It's sort of hard to extrapolate and scale that out when it's already baked into the source code how it should be deployed and how it should run. So we want to allow you to program concurrency and scalability at a higher level. We also want to be able to both scale up and to scale down and to scale like in and out. So we have people running Akka on Android phones. We have people running Akka on huge boxes. We have people running Akka on their normal workstations. And we have people running Akka on a lot of servers. So it's really a paradigm to both scale up, out, and in. And sort of, it's a very flexible way of doing things. And we want to be flexible. We also want to be able to manage system overload. Because, to be frank, if there is a crash in the market and you can't log into your stock exchange to sort of sell or buy what you want to do, it's not like a situation you want to end up in. So managing system overload is an important aspect of building scalable and highly concurrent applications. We also want to be able to automatically replicate and distribute your application so you can sort of scale out in a more dynamic way. You don't have to sort of, as I said earlier, you don't have to hard code that into your application. And the reason is simple. You can't really have any fault tolerance if you don't have any replications, because then you have single points of failure. We also want to be able to automatically load balance the application. This sort of ties into handle system overload, but it's really important because some workloads end up being very sort of targeting one node or a specific part of the system, and to be able to automatically adapt to those scenarios is important. So the question is, how do we achieve this? Well, how can we make a programming model that doesn't really tie these things together and hard code and make everything very sort of robust in a bad sense? Well, what about something called actors? And how many of you have heard about actors before? So an actor, this is an actor, but not technically what I'm talking about today. So in my opinion, a really good actor, but in any case, an actor is sort of a unit of code organization or a unit of computation. And actors, they help you to create applications that are possible to make concurrent, scalable, and fault tolerant. And it's sort of a part of how they are built that sort of lets you to take advantage of this. Well, you can see it as sort of a, like if you go back and see like a unit of code organization. So if you're into the EE stuff, it's like session beans or something like that, but it's a way that makes it possible to not mix concerns in your code in the sense that you would do with locks and synchronize and stuff like that. So you don't want to mix different levels of programming, like coordination with actual business logic with other things. So the actor model allows you to sort of write that kind of programs. So a lot of you have actually already heard about actors, but for those of you who haven't, it's not something new. It's from the 70s, like all cool stuff in computer science that we're sort of rediscovering today. But it's really tried and true. Erlang has been using it since the 80s with great success. And they use it for telecom systems with really high uptime. I have a colleague of mine from Germany, and I've heard that they have other definitions of nines of uptime. Well, you ask, is it up 9? Is it up 9? And it's a different way they do it there, but it's not the same thing. So tying back to raising the abstraction level, like programming at a higher level, don't think in the terms of shared state. Shared state is sort of making the illusion that it's cheap and easy to peer into the minds of others. So it's cheap to read state from somewhere else. It's cheap to update state to somewhere else. That is true when you're in the local virtual machine or very close in memory. But when you have things that are running on other boxes, potentially on the other side of the planet, thinking in shared state means that you have a leaky abstraction, that the optimization of doing things locally leaks out to the assumption that it's the same way for everything else. This is not true. Threads and locks, it's a means of execution. It's not a means of organizing code. So when you write threads and locks, you're trying to mix in execution with logic, with your business logic. That's just wrong. It's completely have anybody of you ever tried to debug someone's really nifty concurrency code? Yeah, how many of you want to do it? 0 for the record. It's not something you want to do, and you're never sure if you're actually fixed or broken something else. And it's just hard to test these kinds of things. Concurrent collections are good when you're local. It's a good optimization. Mutable state is a good optimization when you can keep it local. With actors, low-level concurrency plumbing becomes workflow. You think about how things are flowing in the system, not necessarily how that is actually done. It's communicating intent and not the how. The imperative way is always the how you do it. This is sort of like what. as a consequence of this, you can get high CPU utilization and high throughput and scalability just for the sake of the model, because you're going to use the model in a sense that doesn't make assumptions on how things are done. And it also has a very good way of dealing with failure. Like the actor model has a very good way of dealing with failure, and Erlang has sort of pioneered this in how you deal with failures in a very highly concurrent, a highly distributed system. A lot of things, when it comes to fault tolerance, it becomes tacked on as a sort of an afterthought when you realize that the happy scenario isn't always the case. Actors have a very nice way of dealing with failure that we're going to talk about a bit later. Another good thing about actors is that they are distributable by design. And what do I mean by that? They are location transparent, so it's sort of like you have an identity or something you can address. And it makes it possible to, just as you have a post address, you may live in the same building or you may live in a different city or a different country. It's an address to something that you can send something to. And addresses are provably a very good way of making things distributed. Scaling up and out as a part of the model. I'm going to show you later in this talk how we can both scale up and out, which is the title of the talk. You get a perfect fabric for the cloud, because it means that since you're not encoding in your application how things are done or where they are located, it's easier to just make things configurable and automatic how it will be deployed at runtime. You might have the same application deployed in two completely different sized systems or data centers or whatever, but the important thing, it's possible to optimize for the actual deployment and not change the application to fit the deployment. It's very elastic and dynamic. Message passing, which Actor uses to communicate, is very, very elastic. You sort of send emails every day. It's very non-strict in how you can send email. It's fault-tolerant and self-healing. I'm going to show you how you can make systems that self-heal, so they react to failure and has a strategy for dealing with failure. And you can also do the adaptive load balancing and rebalancing, and also in extension, you can move actors to where they are most used. Just as in your company, you might take your distributed team and move them to the same place for a month or two when they're doing something really important. So this allows you to build extremely loosely coupled and dynamic systems that changes with the runtime. So how does this fit into my building of applications? This is, up until now, it's been sort of really fluffy, high level speak, but how does this relate to what you guys are doing? Well, you can sort of see, like, in different scenarios, because there is always like different way of seeing things, you can have Actor as an alternative to a thread, for instance, a thread of execution, or an object instance, a component of sorts, a callback or a listener, something that you can notify, a singleton or a service, like you wrap a web service or you wrap a database service in an Actor. You could have it like as a router for routing things amongst multiple boxes or multiple other external systems. You can use it as an alternative to a session bean or a message-driven bean. A question I get a lot, like, what's the difference between a message-driven bean and an Actor? The message-driven bean is not stateful, and the Actor can be stateful. Or you can see that just as an out-of-process service, something running on another box and you communicate with it. They're also pretty much described as finite state machines. So we have an API in Akka to really have a good DSL for building finite state machines. So what does the Actor model actually mean? What's the definition of the Actor model? So this is Carl Hewitt, the sort of the inventor of the Actor model. And if you go there, there's a nice talk that you can watch, him speaking about actors. So for him, it's a fundamental unit of computation. So it's computation. It's not a fundamental unit of message passing. So it has processing. It has some sort of storage. So it can store state, be stateful. It has a means to communicate with other actors. So actors can communicate. And there's 3 axioms. So when an actor receives a message, it can either and or, in any combination you want, it can create new actors, sort of spawning new subparts of itself to do work. It can also send messages to other actors that it knows about. And it can send how many messages it wants in an order. And it can also designate how it will react to the next message it receives. So just as you can affect how your coworker will react to the next thing you say by insulting them or giving them praise, you can sort of affect, the actor can change how it reacts to new messages. It's a very flexible way of doing things, and I will show you what that means. So there are 4 core operations to actors, and the 0 here is just because we need some way of defining an actor first before we can actually do anything with it. So we start with a prequel thing, which is called define. And this is my first code slide, by the way, for all you developers. So first we need to sort of define some message that we're going to send. You can send a string or a primitive or something like that, but it's normally good style to define a message. So here we define a greeting class. It's serializable, so the default Akka uses Java serialization when you communicate via nodes, but it's fully configurable, so whatever you want to use. And it just has one field, who, greet who. Then we define the actor class, the actor type. What is the actor doing, this type of actor? Well, you define the class greeting actor. It has, it's extending untyped actor, which is a class that we provide. So there are both typed and untyped actors, but for this presentation we're talking about untyped actors. We define a behavior on receive. So when I receive a message, what do I do? This is the behavioral part of the actor. In this case, we're saying that when I get a message that is a greeting, I will just log that message and log it like hello, whoever I was supposed to greet. Does that make sense? Message class, just a normal class, nothing magical, extends untyped actor, has a behavior for how it receives and how it reacts to messages. Of course, you can do like anything you want in there. The good thing about this is that we are able to execute every actor in a potentially its own thread. So as you can see here, there is no synchronized, no logs, no nothing. There is nothing that indicates how things are being executed. It's just declarative what this actor does when it gets a message. The first operation, now that we have an actor type, and something to send to it, is that we want to be able to create actors. We want to instantiate our actors. So the create operation creates a new instance of an actor. In Akka, it's extremely lightweight compared to threads. So you can approximately have 2.7 million actors per gigabyte of RAM. So when you do thread-based programming, you have to be very, very careful about how many threads you create, because after a certain threshold, you're going to get diminishing returns from context switches. So you can create virtually how many actors you want as long as you have memory for it. They don't occupy any CPU resources if they don't have anything to do. So they're just resident in memory. And it's a very strong encapsulation compared to normal classes, because you will see that how we instantiate this actor, it is very, very isolated from its surroundings. If you see in the previous slide, we had some state here. We had the log, so it can have state. It's a stateful thing. We have behavior. And we have some sort of message queue that makes sure that we get the messages in the receive method. So the messages are received one at a time. This is important. So Akka guarantees that every actor can only process one message at a time. So then you don't have to have any synchronized, you don't have to have any coordination things. It's the guarantee that we give you. And we take care of safely publishing the changes within the actors, so you don't need to worry about unsafe publication on the JVM and other threads not seeing updates. This we solve for you. It's also a tight coupling between state and behavior. So one object, like an object, it has state, it has behavior. And the only way to sort of observe the state of an actor is by sending it a message and query, what state are you in? You can't reach into the head of another person to see, are they happy? You have to observe what they're saying to you. You have to ask, are you okay? So how do we instantiate an actor? Well, Akka has something called an ActorSystem, which is the logical application. So like a Spring context or something like that that encapsulates a logical application. And from that ActorSystem, we can create, using actor of, using something called props, which I think all actors should have. And I think there's only one genre of movies where they don't really need any props. But your actors is going to need some props. You put in the class of the actor. So in this example, we're not showing how you use constructor parameters. So this is simply a definition of how we instantiate your actor here. So we create the ActorSystem first. We give it props, which is the configuration for this particular instance. And then we give it a name when we create it. It has a logical name. This particular instance has its own identity. Make sense, everybody? Everybody with me? Blood sugar is still high.
I had a question. So, can an actor receive multiple messages at the same time?
So the question is, can an actor receive multiple messages at the same time? No. That would be completely entering the shared state synchronized thing again. Yes?
Can a message be a reference?
Yes. So a message can be a reference. And
Does that mean that you can share state between actors?
absolutely, you can do that. So we're trying to design things to be distributed by design and then make optimizations locally. So locally, what Akka does is that it passes things by reference because it knows that it's inside, it knows what it's communicating with, whether it's local or remote. So we can optimize for that because passing reference inside a JVM is extremely fast. But there's an option to turn on serialization of messages even within the VM if you really want to have strong isolation between your actors. So it's up to you how you want to do it. We also encourage all messages to be immutable, just because it's a good sort of standard to have, and it's easier to reason about messages if they are immutable. Does that answer the question?
Well, it's just that if you can share a reference, then it breaks the independence of actors, which seems to be its main advantage. If you can share a reference, then actors are no longer independent of one another.
Yeah, so if you can share references, actors are no longer independent. Well, that's true, but on the other hand, on the JVM, any actor could call system exit at any time, which would kill the entire process. So it's not really something we can solve. Also, even if you have class loader isolation, a lot of stuff are loaded in the system class loader, which is shared. So it's not something we can really solve here, but it's an implementation detail. So it's not inherent in the model that you need to have reference isolation or not. All right. Everybody with me. Now we can create actors. We can define them, we can create them, we can create how many we want, as we have RAM at least. So what's interesting about Akka that Erlang doesn't really enforce, Erlang, by the way, is the Ericsson thing that I talked about earlier with the German nines. So what's interesting about Akka is that it enforces a hierarchy of actors. And this is interesting because when you create an actor using actor of on the system level, it's top level. And every actor, so this is the name, I created an actor called foo. It's created on the top level as foo. But every actor can create other actors, as I said earlier. And if foo creates A, then A is a child of foo. And you can do that like how much you want. But does this structure look familiar to you? Like a graph and a tree? Well, when you have this sort of a tree and every node has a name, you can sort of address it, right? So we know foo, and we know the child of foo A. This means that it's really easy to sort of look at how my application behaves, how it's structured. You can reason about how it's structured. Because if everything is standalone, the human brain is going to have a hard time picturing what it looks like. But when you have this hierarchy, it's easier to reason about, and computer scientists and people using computers have been using file systems for ages, so it's very natural to think about. Operation number 2, send. We have actors. They don't really do anything unless we send them messages, so we need to send something. So the send operation takes a message and sends it to the actor. Pretty simple. In Akka, this is asynchronous and non-blocking. So put the message on, and the actor will process it when it gets CPU time, when it's that message's turn. So it's a fire forget operation. Actors receive message reactively. They react to messages. So there is no tight coupling between sending and receiving. You can see messages as the kinetic energy in the actor system. So actors are sort of passive, or they have a potential energy until they receive a message to which they can react. And in Akka, we try to make everything asynchronous and lockless because we love asynchronous and lockless. You can do a lot of interesting things when you don't risk deadlocking yourself at every corner, right? As an example, part of the goals of this presentation is to show you how we use Java util concurrent. And up until 2.0, we were sort of heavily using this guy, the ThreadPoolExecutor. It has an interesting performance profile, or a scalability profile. This is just our benching things. So if you have as many actors as you have cores and you send the messages all the time, you're sort of saturating the system, right? So what does this look like to you? Is this a good scalability profile? Is this something you would? Yes, that's how it should look. It completely bottlenecks after about 8 actors. And we were sort of scratching our heads because we weren't really expecting this. How many cores? This was an 8-core machine. So it's fairly logical to see how this bottles out. But the interesting thing is that since everything is asynchronous and there's nothing blocking each other, it could essentially have a lot of throughput, right? But this really bottlenecks out. So we scratched our heads and we were trying to debug this, and we sort of found out that the single task queue of the ThreadPoolExecutor is the bottleneck. That's the single point of bottleneck that everyone tries to put things into the task queue. So you cannot scale at all. Yeah? Was it on the 48 core board? Oh, okay. 48 cores. Yeah, this was completely unexpected. So we sort of investigated alternatives to this, and we saw the fork join pool for Java 7. Thought, this looks interesting. It didn't have that good of a performance profile either because it bottlenecked out, because we don't do forks and joins. We can never join messages. There is no join phase. So the fork join pool in Java 7 has a single task queue for external submissions, and every worker thread have a local queue for the locally submit the forks, and then they join that. So we sort of tried to get to the bottom of this, and Doug Lee has improved. So for Java 8, it has a new fork join pool that has this scalability profile. So this is the ThreadPoolExecutor I was talking about earlier, and this is how it looks on the 48-core box with the new fork join pool. A lot better. And this is just using the Akka standard configuration on the 48-core box. And we were sort of, okay, so now we're getting somewhere. So let's see what we can do if we actually try to configure it for throughput. And with just changing some configuration parameters, we got to 50 million messages per second on that box. So Java 8 fork join pool, way better than Java 7 fork join pool. So how do we send messages? Well, it's fairly simple. There's a method on the actor ref, the isolation of an actor. That's called tell. So you tell the actor something. And in this case, we give it the greeting. So this is what we tell the actor. That gets sent to the actor. So this is fire and forget. Just asynchronous fire and forget. So now we know defining an actor, creating an actor, and sending messages. So this is the full example. This is sort of the whole thing. So what we do also, yeah?
In Hewitt's model, when you send two messages, there's no requirement for them to arrive in the same order they're sent. Is that what happens in Akka?
Yeah, so the question is the message send semantics. So in Akka, we guarantee that the order of messages are retained per sender and receiver. So if sender A sends A and B, they will be received in A and B order. But interleaving of other sends is completely non-deterministic in that sense. So, yeah. All right, so we also give sort of a convenience way to reply to messages. So whenever you process a message, there is a get sender, and you can tell the sender a reply. You can do that how many times you want or not at all. So that's how you reply to things. And this, you see the self, get self there, it's who is replying. Because technically you could be forking out, you could tell a bunch of other actors to sort of go and retain the original sender and forward the messages, and then in the end sort of reply once. So there's no hard coupling between sending and replying. Become. So the third operation, in my opinion, one of the most important ones. It's the possibility to redefine the actor's behavior at runtime. Scary stuff, right? So become is naturally triggered by processing a message. So if somebody tells you something bad, you might change your behavior towards that person in the future. Sort of like a type change, if you're talking statically typed systems. It's a type change of the actor. And it will react differently to the next message, and potentially other messages after that. It's possible to stack and push and pop new behaviors if you want to. So it's a behavior stack. And I guess the question you guys have right now is like, why would I want to do that? Seems terrible. Well, in a highly contended system, you might want to change the behavior of the actor to sort of forward messages to other actors to cope with the load. So it's no longer doing the same thing it was doing before, but it's changing behavior to try to provide the same guarantees that it did before, but in another way. Might be a finite state machine. So it's now in another state. It's going to react differently to stuff when it's in a different state. It could gracefully degrade. So if it determines that something it's calling, like it does request to a database, it might say, okay, this database is not responding as fast as it used to. I will throw away every third request, or just say I'm completely overloaded right now, and try to keep the same SLA. It could also mean that you create a bunch of worker actors and you want to use them in different ways depending on what you're doing. So it's a generic worker pattern. I have workers, but I define how they work. Or you can do whatever you want. It's completely up to you. But it's very useful once you get to use it. And this is how you do it. Get context is available inside your actor. So it's the context of this particular actor. And it has a become method. We have something called a procedure, which is a single abstract method interface. Because it simply doesn't return anything, it just side effects. So in this case, we define a new behavior. When we get a message, we will do something else. You could also unbecome to say, okay, whatever I was doing right now, let's stop doing that and go back to what we were doing before. Everybody with me? Yes or no? All right. All right, so there's another one, and I think this is one of the most important ones. It's supervise. So we were talking about fault tolerance earlier and how that's sort of tacked onto things at times. And actors have a very nice way of dealing with failure. So what we can do is that we can have actors supervise other actors. So since we have a tree, right, we can have actors supervising other actors. So like a hierarchical company where you have somebody supervising someone else that is being supervised by someone else. And what the supervisor does is that it detects and responds to failures of its children or its sub-actors. So since you have a hierarchy, all the children you spawn, you're the parent of these children, and you're responsible for supervising them so they don't misbehave. So when an actor crashes, like there is an exception occurring when you're processing a message, that notification of failure will be sent to the parent saying that this child has a problem, what should we do? And then the supervisor decides what to do. And this provides a very clean separation of the actual processing with how you handle the failure. So instead of sprinkling your try-catch block where you're actually doing the thing, it separates the try-catch block from what you're doing. So the child itself does not need to know how it's being supervised. Normal ways, it's like, how do we deal with failure? Well, just run around and scream, right? It's the normal way of dealing with failure on the JVM is sort of like, what do we do when things happen? We just, something bad is happening. Failure management in Java, C, C#, these types of languages is really, you all understand what I mean. Like you have like 4 different levels of try-catch finallys, and like the file close will actually throw an exception, and then you give them one single thread of control in these languages, and once you have your thread of control, it's precious to you. So if things blows up, your accessory is good. You only had one thread, and now it's gone. So you need to do all this try-catch in every place, and you don't really know what kinds of exceptions am I supposed to handle. It's like, yeah, if I use checked exceptions, I might get those, but I also might get the runtime exceptions. And what do I do? What kind of runtime exceptions do I do? And it sort of becomes very messy because you are responsible to handle your own failures. And they don't propagate. Even if the exception goes to the top of the thread is dead. Who do you notify? This thread died. All right, what do I do? What did it do? How do I resurrect a thread from the dead? You don't do that. So this leads you to this try-catch stuff. You tangle everything up. You try to protect your precious thread, and it gets scattered all over the place. Your business code has the try-catch blocks, it has the synchronized blocks, and you have like all different concerns in one place. So there is a solution to this in what's called the onion model, or the onion layered model, or as the Erlangers usually call it, the error kernel. So you try to structure your application where you push risk down in the layers. So you have one core, which is very, very dear to you, and if that core blows up, the application is hosed anyway. So you try to push the risk out to others, to isolate the most precious thing from the worst thing. So what does this mean? Well, you have like a error kernel. Let's say that this is the top level actors that we created using system actor of. And these are the children that they created. So this is the hierarchy. And the things at the top, if they blow up, your application can't continue anyway because it's so severe it can't recover. But if a child blows up, something happened, it notifies the supervisor, and the supervisor can decide to reinstantiate, resurrect this child. But it also means that if a child blows up, the supervisor could say, I will kill all my children and restart them all anew. And it goes up in the hierarchy. So if a child blows up, the supervisor determines, I can't handle this. This is completely over my head. I need to escalate to my manager, and he will sort of try to deal with this very, very severe problem. So it means that you can push risk. I have a risky operation. I will create a child, and he will do the risky operation. I don't risk my stuff. I just let my kids do the really dangerous stuff. By the way, this is not parenting advice. Only use it for actors. What's interesting about this, though, is that you can supervise things over nodes, over physical nodes. You can have parts of your application running on different physical nodes and supervise and deal with that over nodes. So, how do we supervise actors? Well, every actor, as I said, supervises its children, and there is a default parenting strategy, but you can override this. So just to break things down, we define a supervisor strategy, in this case a one-for-one strategy, which means one child dies, that child gets handled. There's also a all-for-one strategy that deals with all children if one fails, because they might be interconnected in some way. This is the 10 there is how many times it's supposed to be restarted. So how many times am I going to apply this to this child? And within which time frame. So you can sort of say that if this child fails at most 5 times per minute, then that's acceptable, because I might have an unreliable input source of sorts. But if things just blow up all the time, things are getting bad, and I need to sort of deal with that. So, for every child failing, you get the exception, what happened, and you can say, okay, if it's an arithmetic exception, I will just resume the child. It was trying to divide by 0. Let's just let it be and let it continue. If it was a null pointer exception, there might be some state within the actor that is broken now. So we issue a restart, which means that take your current instance of this actor, throw it away, re-instantiate the actor with what you provided in your props. So if it was created using the class, it will be recreated. So you re-instantiate it in a known-to-work state. Really important. Or, as I said earlier, you can escalate it. I can't handle any other exceptions than these. So if there's something else, I need to escalate to my parent. And then you need to override the supervisor strategy method to say, this is my strategy. When I create a child here, the worker, I will just forward messages to that worker. And this is just an actor. The other thing is just an actor. The worker, in his turn, can also be a supervisor for his children. He is a supervisor for his children, but he might not have any children.
Are those 3 methods, resume, restart, and escalate, are they predefined or do you define them?
It's defined in our framework. So we provide what possible operations are. Yeah.
So if it's a distributed system, right, and it's a network partition anticipation where the parent is separated from the child, I assume the parent gets indication of some sort of network.
All right. So in the event of having a net split or a partition network, how is that handled in terms of supervision? Well, it's sort of, I'm going to talk about more the clustering stuff later, because you can't know from within the system the status of the other system. That's a normal problem of this. So what we have there is that you will have to define a formula for when you determine that this thing is dead.
Well, does the child also get some information, some indication that, well, he should probably stop doing what he's doing because the parent would maybe restart the whole operation without the child.
I'm sorry, I didn't.
Shouldn't the children get false notification, that he's now parentless?
Okay, so if a child on another node become logically parentless because the parent was living on another node, then that will be notified and handled by the system for at least for 2.1 at least, because it's really difficult to say, when do you say that the parent is down? Because it could be just an intermittent network failure. But we can discuss this more later because it's a really interesting topic.
Is there a convenient way to find specific actors?
If there is a convenient way of...
Service discovery or something like that?
So what we have right now, I will come to a part of this of the answer to that. But the question is regarding discovery, service discovery or actor discovery. And I'll address half of it, and then afterwards we'll talk about the other half, because that's coming in the next version. Yeah.
On death of an actor, one of two things is true. Either something external to that actor just died, in which case you might want to retry on that same message, or it's divided by 0, and if you spawn more actors, you're going to divide by 0 every time. So if you have any way to control whether I'm going to retry on that message.
Yeah, so the question is regarding message retries. So what we do out of the box is that we discard the message, because it could be a poisonous message. It could be really broken. What we allow you to do is to configure per actor if it should be possible to retry a message or not. And we call that the stash. You can stash away a message and reapply it later. Yes?
What if there's this null pointer exception and it happens deterministically?
If there is a null pointer exception and it happens all the time, well, you saw earlier that I said at most 10 times per minute the actor can restart. So that's how we sort of try to throttle restarts. Yes?
Maybe you've already mentioned this, but just in an ordinary actor tree, if a parent dies, how does the grandparent deal with the children of the dead parent?
Yeah, so how do you handle sort of the escalation of failure? So what we do by default is that we kill the entire sub-hierarchy because they can't exist without their parent. So otherwise you would end up in a weird state, right? So what we do now is that when you escalate, it's the same as saying, okay, this instance with its children is not really working anymore. All right, I need to continue. We will have some more questions later. I just want to make sure that I get through everything. Awesome questions, by the way. And yeah, this is just moving things up so everybody in the back can see as well. We also have some callbacks that you can define on your actor. Let's say you have an actor that makes a really expensive connection to a database, and you want to sort of clean that up before you restart. So you can hook in, okay, what do I do before I'm restarted? I will close this file, or I will close this database connection. I will clean up. And then you can reinitialize afterwards. So this is a hook-in system for dealing with restarts. All right. Routers is a special cased type of actor. And an actor normally on a commodity box, like a 3 gigahertz Intel something or an AMD processor, do around 3 million messages per second. So sometimes that is not enough. So what we have is routers, which makes it possible for a very quick bypass of the mailbox of the router to just send it to one of its children instead. So instead of having the mailbox of the router and everything going through that, we sort of try to avoid the router's mailbox and send it directly to the children. So it's for high performance stuff. But it also allows us to do things like round robin routers, where I will send messages to this child, that child, that child, that child, and then the first, this, that. You can completely define this in your prop. Say, this actor should be a router, and it should be a round robin router, and it should have this number of instances of children that it will send to. So this is the type of the children in this case. So it's logically an example actor, but practically it's multiple. There is a whole host of different types of routers, like random routers, consistent hashing routers, scatter-gather routers, stuff like that for particular use cases. You can also have this dynamic. So how many members, how many children do I have in my router? So you can grow, you can have a lower bound, an upper bound, you can have different sort of parameters for how you should resize this pool of actors. But the interesting thing here is that Akka has a configuration system, so you can, outside of your application, you can define this. So this is a deployment detail. I have a big box, I can run a lot of these. I don't want to change my application code just because I happen to run the same system on differently sized data centers or differently sized servers. It's a complete no-brainer because it makes it completely impossible to test all these combinations. So it's possible to define outside what your deployment scenario is. So here we can say this path of actor. So whenever I get this actor, it will be a round-robin router, and it will have 5 instances. You can also define a resizer for it to be elastic in that sense. But what's even more interesting is that you can, in your configuration, you can specify that this actor, when I create it, I will create it on another box, on another Akka machine. So we first have to define that we're using remoting, so it's not just a local system anymore. For our greeter that we created first, when we create that greeter, it should be remote, and it should be remote using the Akka protocol on that actor system on this host machine using this port. So if you run Akka over there, you have the possibility to deploy your actors on different machines. This all was Akka 2.0, so this is already out. It's been out for more than half a year. And in a couple of weeks, we're going to release Akka 2.1. And what's interesting about Akka 2.1 is that we're shipping Akka Cluster as an experimental module. So we've implemented our own clustering, which is based on the thoughts of React and the Dynamo paper, to make it possible to have clustered actor systems. And to enable this, it's fairly simple. Just as we said earlier that we were using remoting, now we're saying we're using clustering. And we have a couple of seed nodes that you try to connect to initially that just bootstraps everything. So it's completely peer-to-peer, and it's gossip-based. And we're also, the reason it's experimental is that we're not sure if the APIs that we provide are the right APIs for what people are going to do. So we want feedback. We want people to try this out and give us feedback so we can make sure that for 2.2 we have the right APIs and we have the right kind of functionality that people need. So with Akka clustering, we can define that our router is now a clustered router, and it will be running max number of instances per node, and it will allow to have local copies of the thing. So you can really tailor the deployment of the actor for when you're actually using the system. If you're more interested in the clustering and how we've built that, in case you're that kind of person that finds that interesting, we have a white paper about how we're doing things. We have documentation on how you're supposed to use it. And we also have the code if you want to take a look and dive into the deep end. Also, with 2.1, we have Akka Camel, which is our sort of bridge layer for using Apache Camel using actors. So you can route to actors, and you can route from actors. So you can use Apache Camel with actors and address actors and use actors for building up your workflows and pipelines. And this allows you, I don't know how much of you know about Apache Camel, but it has like 100 different connectors to different types of software and protocols, and it's like an enterprise integration patterns package. So this really allows you to make Akka a part of whatever infrastructure you already have. What's new also is the Typesafe console. We have a console for using the Akka, and so you can monitor Akka. It looks like this. I wasn't really sure that the Wi-Fi was going to work for me, but there is a link later. So this is how you monitor an Akka application. So we allow you to see what actors are running, what kind of problems are happening, etc. You should definitely have a look. It's a really neat piece of software. There's a live demo in case any of you have internet access. You go on to consoledemo.typesafe.com, log in, check it out. It allows you to see a lot of interesting metrics about your present applications. So what kind of message rates, traces of messages, the latencies, and latency distributed like a scatter plot thingy. You can see your tree, the queue sizes, average queue sizes of your mailboxes, and average throughput, and a lot of all this metric stuff that are really interesting when you're both running an Akka application and when you're developing and debugging against an Akka application. But there's so much more. I want to make sure that we have time for questions. I just want to make sure that there's a lot of stuff to Akka. There's We have typed actors, we have data flow, CRMQ integration, we have something called extensions that lets you write your own integrations with Akka. A lot of stuff. So there's a rich sort of ecosystem around it. This is where it's at. So akka.io is the site. We have a team blog at letitcrash.com. And this is the Typesafe site where you can find out more about the console. And I also want to mention that we have a Typesafe developer contest starting now. So we are looking for awesome examples of how you can use Akka and Play and Scala to build cool applications. And there's some fabulous prizes that Martin Ordersky has donated for promoting this. And you can read more about it there. And this is all I had. So I'm sure there's a lot of questions right now, and I'm really glad that we have like 5 minutes to go. So shoot. Yes?
Are message queues infinite, or are they fixed length?
So if message queues are unbounded or something else. So by default, we use a concurrent linked queue, which is really fast, low latency, and it's thread safe. But you can define either per actor or per group of actors what kind of message queue you want to use. You can even use your own implementations, you can use durable versions, or you can even use like a broker and have a broker handle it. So we really separated the transport and the delivery from the actual model. So you can completely hook into that. Yes?
Are there design patterns for how to use all of these actors?
Yeah, so if there is design, you should really go into letitcrash.com. And there's we had like a Akka summer of blogs, so there's a lot of interesting blog posts on how you can use actors in different use cases. That's a really good resource for that. Yes?
What do you do with 0MQ?
What do we do with 0MQ? So some people have like a very heterogeneous system. So they have some C stuff, they have some Python stuff, and they use 0MQ to sort of integrate. And that is what you use the 0MQ integration. So if you want to communicate with other 0MQ systems. Yes?
How do you manage threads on an EE container?
Okay, so how do you manage threads on an EE container? So what we allow you to do is that Akka's shipped with different thread pools and how you can configure them in the configuration file. But you can write your own provider. So if you want to use container managed thread pools, you can just do your own wrapper and load that into Akka, and you can use it as you would use any other container managed thread pool. Yes?
You mentioned resume. What do you do on resume when there's a failure?
So resume, what we do when you resume an actor is simply as you were. It's simply just a OK to continue processing messages.
But then the message was interrupted in some place and you threw an exception. What do you mean continue processing a message?
So
the one that failed? How do you return away?
No. So we throw away the failing message by default. Okay. If you want to reuse, you can stash that message.
Right. And then you mentioned Resizer. How does it determine it's time to resize up or down? Yeah, so
the Resizer, there's a default one which was in the code. There's a default Resizer that has a lot of different parameters that you can tune how and when it should resize. So you should really look at the docs because it's really rich in that sense. But you could also write your own.
Right.
Yes?
Are a lot of people using agents?
If a lot of people are using agents, well, I know that just a couple of days ago, Cloud was writing a blog post on how they use futures and agents with Akka. So they have like 1 billion API calls a day or something. So there's quite a few people that use that. But since STM isn't distributed, you have to know what you're getting into, because the model of STM means that you're going to use shared state. That's sort of the point of it. So it's good for certain use cases. And that's sort of what Akka tries to do is there is no one tool will fit all use cases. So whenever you find a good fit for agents, just go ahead and use agents. And don't use them if it's not the best choice. Yes?
Since you can pass references around, what happens when you're passing your reference to an actor which is on a different machine?
Yeah. So since you can pass reference around, you saw the actorref thing that was returned by the actor of call. That is transparently going to be converted to a remote version of that reference when it crosses the boundaries to another system. So we serialize that to be a remote representation, and when you get it in, we see if it's a local one or if it's still a remote one. So it's sort of transparent in that sense.
But that will change the semantics of what you're doing. I mean, unknown to the programmer, if the two actors are on the same machine, then they're dealing with a real reference. But if the two actors are on different machines, then you're dealing with a copy of the
Yes,
reference.
but the only thing you can do with an actor ref is send it messages. So there isn't that much things you can assume about it except for you send it messages.
No, I meant the reference to the data which you passed in the message.
Immutability is
Yeah.
encouraged.
Yeah.
The message itself.
So the message itself, of course, if you have mutable messages, you've already said that I'm going to do this. So there's really nothing I can do to prevent you from it. But I can encourage you to use immutable data and sort of choose a serialization mechanism that will fit your use case and like performance and network-wise. So it's flexible in that sense. Yes?
Do you do flow control across here, so queue to queue, someone is throwing too many messages, stop doing it?
Yes. So flow control, it's sort of a problematic area in a distributed sense. But if you're doing local stuff, you can have bounded mailboxes and have that either drop the messages or have back pressure. But back pressure only makes sense if you're local, because having back pressure over a network connection where the back pressure is only actor to actor, is sort of, you would essentially have to have one connection per actor, which wouldn't really scale. Yes?
Are there exemplary open source projects that use Akka that we can review to learn more about?
Yeah. There's a lot of examples. So there was a student at University of Illinois or something that sort of did a write-up on all projects on GitHub that use Akka, which was quite of an extensive list. So if you Google like Akka example projects or something, you should be able to find it. Anyone else? Yeah?
Diagnostics of how to diagnose the issue if you've got, queue length increasing,
Yeah.
what do you do?
Yeah, so that's where the issue debugging thing, when you have performance or that sense of problems, that's when the console really shines, because you can see what like the average size of the mailbox is, what kind of throughput you're having, and what kind of average latency of each message you
Yeah,
have.
but what do you do to solve the issues? Because let's say if there's contention on a log, I have a list of strategies I can apply, like strap the log, think about doing some concurrent coding. What can I do here?
No, you can hook in whatever mailbox you want. So you can deal with it in any way you want. So when you have contention, it's completely open in that sense.
What I mean is, if I had a system built on logs, right?
Yeah.
Then by looking at latency, I could determine where I need to pay attention. System self-throttles,
Yeah.
and I can address the issue. I know how to do it. But then if I'm passing messages,
Yeah.
same problem is reformulated in terms of queues. How do I solve a problem when I have a queue? What methodologies?
Yeah, so what you can do there is either you have to decide, do I want to spend more processing time processing messages? Do I want to split up in more actors? Or do I want to... It becomes a more distributed problem. Like how do you deal with a distributed denial of service attack? It's essentially what you're saying. How do I prevent myself from a...
Yeah, okay.
Yeah. Anyone else?
Last one. So, is there any concept of fork and join between these actors?
If there is a concept of fork and join within actors, not per se, but you can definitely use actors to form fork join behavior. But I normally recommend...
Provide the exact parallelism. It might provide the concurrency, it might not provide the parallelism.
So what I recommend for fork join types of operations is using futures, which is a very nice way of doing that. So with Scala 2.10, sort of the Akka futures has been sort of merged into the Scala standard library. We've had, it's like a JSR for futures, and like we have Twitter and everyone try to harmonize on one single implementation. But I really recommend using futures for that sort of thing because it's so easy to reason about. Yes?
Is the Java security context pushed between threads?
So if Java security context is pushed between threads, no. Mainly because it's really tricky once you go over nodes. But of course you could hook into your own, you can write your own message dispatcher that runs the actors and hook into that and propagate between. So in 2.10, Scala 2.10, Akka 2.1, there is something called an execution context that you can hook into and before you jump, you can set the thing and reset it on the other side. So you can sort of get the same behavior, but it's not, it's a tricky situation.
So could I do something to scale to 9?
Yeah, you could always do the message dispatcher approach where you sort of restore, save and restore the context, or you just capture it within the actor itself, because I think somewhere the context has to come from. So how does it relate to the message, or does it relate to an actor? So you have to see how you structure that. Yes?
And a related question, do you do ActorSystem protocol?
ActorSystem?
Yeah, like Akka.
Secure Akka. Yeah, well, so what's interesting about 2.1 is that we support SSL and TLS for remoting now. So you can pick and choose whatever ciphers you want to use. So you can have ActorSystem.
Okay.
Yeah. All right?
Can you show the first slide with your name?
The first slide. Let's see if I can do that. I don't want to. That's me. Thank you.